Hello physics students. Today I'm going to talk about why the outcome of some collisions can end up different even though the objects began with the same initial conditions. To illustrate what I mean, I have again my two cars here on this track, and again we're going to assume it's isolated in a horizontal direction. There's no friction in the bearings. So in the first case, what I could do is I could shove this car forward and have it crash into that car, and since they have Velcro facing each other, they're going to stick together. And then the collision looks like that. So again, car at rest, car comes in, and they stick together and move together slowly after the impact. Or what I could do is shove this car the same way, but what I'm going to do is tape over the Velcro so that the cars cannot stick now. I'm going to push this the same way, or try to push it the same way. This is still at rest, so we have essentially the same beginning conditions. And now you see that the cars bounce with a slight bounce, and they separate because the Velcro was not able to attach. Or I could, if I want, make them collide with the spring, and then you'll see even more bounce this time because of the spring. And finally, if I want, I could have these collide in such a way that they never touch. You might say, well, that's impossible. If they don't touch, they don't collide. What I have here are two magnets that are repelling each other, and I can't push this very fast because the cars derail, but I could create a collision where the bounce is in a sense like perfect, where the cars don't even ever touch. They come together and repel away. So the same initial conditions, at rest, shoving, and multiple different outcomes. So we wish to describe how these are different in terms of the physics that we know so far in the course. The first point is that momentum is conserved in all the cases. No matter what I do in terms of their interactions, the blue car pushes the red car forward with some force. The red car pushes right back with the same exact force. That's Newton's third law, a law of nature. It cannot be violated. So that means the impulse this way is equal to the impulse that way. Changing the impact structure merely makes one car gain more momentum and the other one lose more in the different scenarios, but still the gain of one car is always equal to the loss of the other, meaning the system has no change in momentum. The difference in these collisions can be summarized in terms of the energy, the other kind of conservation that we learned about. So P is always conserved. We're going to find that the energy conservation is a little bit different. So the way we categorize these different kinds of collisions is with the terms elastic versus inelastic collisions. And the first point I want to make is there's not one or the other. On one end, there are what we call perfectly inelastic collisions. At the other end of a spectrum are elastic collisions. You don't need the word perfectly with elastic. Elastic already tells us it's a perfect kind of collision, the other extreme of this kind of perfect collision. And in between are inelastic. So what we mean by a perfectly inelastic is the case where the objects stick together upon impact like the Velcro. That's the furthest extreme of all these different kinds of collisions, where they stick together and move as one. So that's over here. So as I said, momentum is still conserved. Pi is still equal to Pf whether you have Velcro or magnets. What's different though is the kinetic energy. The kinetic energy before the impact is greater than the kinetic energy after the impact. You might be saying, well, wait a minute, I thought energy was conserved. And you're right, it is. Even in this collision where they stick together with Velcro, energy is conserved, but kinetic energy is not. Why? How can that be? Well, this car comes in with some kinetic energy, and after, that's the initial. The two cars do have some final kinetic energy, but there were other kinds of energy that were produced because of the impact. There could be work. Well, not so much with these cars. What I mean by work is when you have two cars in real life crash, they get dented up. Denting is work. You may not realize this, but let me imagine this is a car, and I want to dent it, crush it. So, and I'm not going to do it with an axe, I'm going to do it with a machine. I put a big giant hydraulic press here, and I put a force times distance. See, force times distance, and I'm crushing this in. That is a joule. That is energy. So when cars get crushed, that took energy. Where did that energy come from? It can't come from just nowhere. Energy is conserved. It came from some of the original kinetic energy. And then there could be heat, sound, and other kinds of energy that are produced. So the total energy is still conserved. If you add these all up, you still get the original kinetic energy. But it's just that some of the kinetic energy was converted, so the initial is greater than the final kinetic energy. Now, so that's perfectly inelastic. Oh, by the way, if you need a moment, let me create a pause for you to catch up copying that down. Okay, so the other possibility is you're somewhere between the perfect balance, and I'll talk about the perfect balance in a moment, but then it's just inelastic. In other words, there's an imperfect bounce. They bounce like when I put the tape next to each other, and then they bounced, and they did not bounce with like a springy situation. But even the spring involved was also inelastic. I'll explain in a second. Pi is still equal to Pf, just like over here. And kinetic energy initial is still greater than kinetic energy final. And the same comments apply about how the kinetic energy went to other kinds of energy, but all these added together still equal. So total energy is still conserved, kinetic energy is not. The difference is that we lost a lot more kinetic energy here. Maybe we lost 50% of the kinetic energy here. Maybe here we only lose 20%. It's less of these because more of the energy is preserved as kinetic energy. And finally, at the furthest extreme over here, so this is no bounce, a bounce that's not perfectly efficient, and then a 100% efficient, perfect bounce, elastic. And that is achieved either through magnet-magnet collisions, where there's actually no physical contact, or charge-charge. Maybe I put a bunch of electrons here and a bunch of electrons and they repel each other. Same kind of idea. Or we have what's called an ideal spring. No such thing, but this kind of magical spring that never loses energy, never creates any heat or anything like that. Pi is still equal to Pf, like all the other kinds of collisions. The difference is kinetic energy initial equals kinetic energy final. No other energies produced. Sound, you shouldn't hear the collision. They shouldn't collide and dent each other's the objects. All of the energy stays as kinetic. Now, to give you some numbers to make sense of what's going on, so let's suppose I have blue car coming in, right, and it's heading toward the red car with 10 joules. You know, whatever, I made up a number. I calculate 1/2 mv squared and I get 10 joules. And the red car's not moving, so it has 0 joules. And then it's going to come in and crash. And then let's suppose they stick together. And so now they're both moving with a kinetic energy, same speed. This one has more because it has more mass in 1/2 mv squared. And so maybe something like this happens. Maybe the blue car now has 1 joule, the red car has 3 joules. Okay? So we're missing some energy. We only have 4. And over here we had 10 in the beginning. Well, because we haven't considered the other kinds of energies, the losses, we could say, the sound, click, the heat produced, the cars getting dented, you know, all these other things. When the cars stick together, there's all these other energies. But notice, again, as I said, total energy is conserved. We had 10 before, and we've got 10 after. It's just that not all of it's kinetic energy anymore. Some of it went into the air or whatever. Okay, so that's an example of a perfectly inelastic with some numbers, hopefully make it seem a little bit more sense. So now let's suppose I put tape on and I make, or even the springs, so they're going to bounce now, and so they're going to go like this and spring apart, but not perfectly efficiently. But I send this car in again with 10 joules, and this one's still not moving. So same thing before, but now I have a little spring in here. So what's going to happen, or a possibility here, is that the red car will go forward and the blue car will bounce off backwards, as we saw in the demonstrations earlier. And you see, so now we have 10 joules before and 7. We're getting closer to being equal, right? But we're still missing some energy. So before we were missing 6, now if you notice, we're missing 3. We have 7 here, 10 here. So now 3 is going into the air as sound or heat, or maybe these get dented, and so that takes some energy. So the, quote, loss, it's not really lost, but it's lost from kinetic energy is lesser amount, okay? And then finally, I send this car in the same way as before, but now I'm going to do maybe magnet, so it's like a perfect bounce where there's no loss. And so what might happen now is that maybe they bounce like this, and the red car might have 7 joules and the blue car has 3 joules. And by the way, people might be saying, shouldn't it be -3 because it's going backwards? Kinetic energy is never negative. It is not a vector. If you throw a baseball this way with 10 joules of kinetic energy, then throw it that way with 10 joules of kinetic energy, it's 10 joules either way. So this does not get negated. It's still positive amount of energy. So now you see with this perfect bounce, the blue car had all the kinetic energy, 10 for the system, and then after, some of it got transferred, but the system still had 10. In other words, no energy leaked off into the air as sound or heat or work to crush these. So it's a perfect bounce. All the kinetic energy is preserved, no other kind of energy produced. So that's the those are the concepts behind these kinds of elastic, inelastic, perfectly inelastic collisions. It's all about how much kinetic energy is preserved, but momentum always preserved, okay? So that's the key. Now what I'm going to do is show you a kind of calculation example that you might encounter with this concept of elastic versus inelastic collisions. So I didn't give a pause yet, but if you need a moment, I'll create a pause to allow you to copy down the other board over there. Okay, so let's move on to that example. Okay, so if you need a moment to catch up copying that down, I'll create a pause. Okay, so you might recognize this as the problem we did in the Momentum Conservation 1 video. So it's the same one up to part A. I did that because, well, it's kind of like, maybe like music, like when you have a song you like, you play it again and again. This is a nice problem, so let's play it again, the solution out. So as always, what we're doing when we use a momentum conservation calculation, we're starting by sketching a diagram. Before and after. So what we have is the 0.5 kilogram car moving at 10 meters per second. Momentum and velocities, they're all vectors. So let me call this positive 10 in this direction, and then 1.5 kilograms at rest, which is 0. After the impact, as you can read from the problem, this bounces west the opposite way. So we need a minus sign because east was positive, west has to be negative. So we don't know that velocity. So there's a diagram laying out all the information, setting up our solution nicely. We begin with one of the two main ideas in this unit, that momentum is conserved for an isolated system. Can you state the first main idea, the other main idea? Well, hopefully you can. It's that impulse, which is force times time. That's the definition. What it does is it changes an object's momentum. So this and J equals Ft equals delta P is the other main idea. Don't forget about that idea and problems with that idea. All right, so let's continue on. We're going to do momentum of the system before. The only thing moving is this. This has no momentum. 1.5 times 0 is 0, so we don't even have to factor it in. We're going to go 0.5 kilograms times 10 meters per second equals, on this side, the 0.5 meters per second, kilograms times the negative 2 meters per second plus this MV, 1.5 kilograms V final. So this is 5, this is negative 1, and that's 1.5 V. Add 1 to both sides, we get 6 equals 1.5 V. Divide both sides by 1.5, and you get V final equals 4 meters per second. Okay. If you need a moment to catch up, I'll create a pause to allow you to copy that down. Okay, moving on. What I just erased was to determine the percent change in the kinetic energy. Well, to get the change in anything, you have to know what you had starting off and what you had at the end, and then you could subtract the two. So I'm going to calculate initial kinetic energy, then I'm going to calculate final kinetic energy. So KE initial, well, KE is always 1/2 mv squared. And so I have 1/2, 0.5 kilograms, 10 meters per second. And what I get is, well, maybe I'll do it here. That's going to be 25 joules. So just sort of highlight that a little bit. The final kinetic energy, what I'm talking about is for the system. And if you look at this picture, yes, in the beginning, this was the only thing that had kinetic energy. This did not. 1/2 m0 squared, 1/2 mv squared was 0 kinetic energy. But over here, I've got kinetic energy here, and I've got kinetic energy here because both of these are moving. This is 4 meters per second, right? So now I have to, for the system, do 1/2 mv squared plus 1/2 mv squared. Maybe we'll say this is the 1 and 2, right? And so 1/2, 0.5 kilograms times 2 meters per second Now, some of you might be saying, if you're keeping up with the writing, you might be saying, wait a minute, I thought you need a minus sign here. You know what, you could put that in. But again, it doesn't matter because you're squaring it anyways. 2 squared is 4, negative 2 squared is also 4. Remember, kinetic energy is never negative, it's always a positive, it's a scalar. If you accelerate your car going north, you burn a certain amount of gas, that's the 1/2 mv squared. Turn around, accelerate, and go south. It's not like suddenly your gas tank's going to fill up and you took negative energy, so you're gaining energy. No, you're still going to burn gas. Going south, north, it's all kinetic energy positive. It all burns gas. So it doesn't matter that it reversed direction. So you punch this on your calculator. This is 1, and this is 12. All adds up to 13 joules. Is the final kinetic energy of the system. So see, if it were a perfect bounce, we would have gotten 25 here. But we don't, because it was an imperfect bounce. So we, quote, lost kinetic energy to other forms. Specifically, we lost 12 joules to other forms. But they ask for the percent change. So this is kind of like a percent error. We could say percent change, I'll write it like this, will be K final minus K initial, the delta, oops, KE, sorry. All over the original KE initial. So again, it's like a percent error. And then so we'll multiply that by 100%. In other words, the final was 13 joules minus the initial, which was 25 joules, all over the initial of 25 joules times 100%. So I think that's negative 48%. So almost half the kinetic energy negative was like a loss. The percent change was negative. So that's how we would calculate. So if you need a moment, I'll create a pause and allow you to catch up with the notes. So if this was an elastic collision, we would have gotten, as I said, 25, 25, 25 minus 25 over 25, 0. We would have gotten 0% change because all of the energy stayed kinetic. But since we see that some of the energy went away, we don't have the same initial and final, we can say that this is an inelastic collision. Why? Because KE initial is greater than KE final. All right, so I'll create a pause to allow you to catch up with that one final piece there. Okay, so there it is. By the way, I want to mention briefly that it's possible to gain energy in a collision, gain kinetic energy. And the way that that might happen is if the cars maybe explode on impact. The extra kinetic energy then released comes from the gasoline. The chemical energy blows it outward, and now we have more kinetic energy, maybe 25, and then all of a sudden we have 100 now or something like that. So only if there's some kind of explosion or release of energy. Otherwise, in all of the cases, kinetic energy initial equals kinetic energy final is the closest you could get or the best you could get, or the kinetic energy initial is greater than kinetic energy final, as we saw in this calculation. But always I want to emphasize Pi equals Pf for all the kinds of collisions as long as the system is isolated. But even if it's isolated, the kinetic energy might not equal out because we get other forms of energy. So that's elastic and inelastic collisions. I hope you found the video informative, you found the demonstrations enjoyable, and I'll see you in the next physics video.